Myself, Dr.Biswambhar Mohanty. Today we will discuss the rotational motion, chapter rotational motion. In rotational motion, first of all, we discuss what is the difference between translatory motion and rotational motion. Translatory motion is rectilinear motions. That is a straight line motion. Suppose a body shifts its position from A to B. That is, its center mass move along this straight line. Center mass means almost all the masses of the body are supposed to be concentrated. That is called center mass. And that is the straight line motion. That is the center mass moves along this straight line. That is the translatory or straight line motion, rectilinear motions. So in this translatory motion, center mass moves along this straight line. What is rotational motion? In a rotational motion, suppose this is a body, suppose this is a rod, and this rod is rotating about this axis. Having certain angular velocity, the rod is rotating about this axis. That means each particle, this rod is moving in rotational motion about this axis. That means each particle on the rod makes a circular motions about the axis of rotation. Each particle of the rod makes a circular motion about the axis of rotation. So difference between rotational motion and translatory motion, that means when a body makes a rotational motion, that means the body means we are discussing the rigid body. Rigid body means the body, the distance between two molecules or two particles remain unchanged even after the external force is applied or external torque is applied. That is called the perfect rigid body. So we are discussing the rigid body means rigid body. So whenever the body makes a rotational motion about a particular axis, then each particle of the body makes a circular motion about the axis of rotations. So that is the difference of the translatory, basic concept of the translatory and rotational motions. And this is the combined rotation. Suppose it is a spherical body. Suppose this is a spherical body. When the spherical body rolls from one position A to position B, and this is the example of both combined translation and rotational motions. This is the translatory motion, this is the rotational motion, and this is the combined translatory rotational motion. This is a combined translatory and rotational motions. So this is the combined translatory rotational motion. In this case, the center mass of the body rolls from position A to actually rolls on a horizontal surface from position A to position B. Then the body makes a rotational motion about the center mass. Body makes a rotational motion about the center mass, but the center mass make a translatory motion. So this center mass makes a translatory motion And the body makes a rotational motion about the center mass. This is the combined translation and rotations. Then we'll discuss the moment of inertia. It is the property of the body by virtue of which the body is unable to change its state of rest or uniform rotational motion without the help of an external torque. So it is the property of the body. It is the property of the body by virtue of which the body is unable to change its state of rest or of uniform rotational motion without the help of an external torque. So as you know that whenever the body moves along a translatory motion, it is possible because of the force, external force. Translatory motion is possible because of the external force. So whenever the force is applied, the body makes a translatory motions. That is what body makes a translatory motion because of the external force. But in case of rotational motion is possible because of the external torque. This is the force into perpendicular distance about which the body is rotating. So tau is equal to r cross r, this is the external torque. And not only because of the force, the rotational motion possible because of the distance, perpendicular distance to the point of application of force to the point about which the body is rotating. So always most important point is torque or angular momentum, we'll discuss the later on, has to be calculated about an axis, about a point. Torque or angular momentum has to be calculated about an axis or about a point. So that is there is the external torque is the property that is the property body by virtue which the body is unable to change its state of rest or uniform rotational motion without the help of an external torque. Without the torque, the body, if the body is at rest, then it will be at rest. If it is moving with a uniform motion, angular motions, a uniform rotational motion. Uniform rotational motion means with a constant angular velocity. It will remain as such without the help of external torque. And it's a moment of inertia. This is the rigid body. This is the rigid body which contains the number of particles M1, M2, M3, M4, M5. And these are discrete particles. What is discrete particles means the particles are actually not connected, which are these called the discrete particles. And momentum inertia I is equal to, this is R1, this is R2, this is the R3. This is the conceptual definition of momentum inertia. This is the conceptual definition of momentum inertia. So M1, M2, M3, this is the M3, and this is the distance R3, this is the R4, and this is R5. And the body is rotating about the axis XY. This is the physical definition of momentum inertia. I will express mathematically. So this is the moment of inertia and the body is rotating about this axis. So that is the I is equal to moment of inertia of the body about the axis xy. The momentum is to be calculated about an axis. Xy is equal to m1 r1 square loss m2 r2 square loss m3 r3 square. So I is equal to so I is equal to m1 r1 square, m2 r2 square, m3 r3 square, m4 r4 square. So I is equal to, we can write it as summation mi ri square. So this is the moment of inertia of this particle, number of particles of the rigid body above the axis of rotation. So moment of inertia is to calculate it actually about an axis of rotation. So for one particle, single particle, so one particle is rotating about this axis. This is the R. So its moment of inertia of the particle about this axis or rotation. That will every particle, the moment of inertia you calculate about an axis. If the axis of rotation will be changed, then moment of the same body will be different. So I is equal to mr square is the momentum of one single particle. So momentum inertia of physical significance is plays the same role as mass in translatory motions. Momentum inertia is the physical quantity plays the same role as the mass in translatory motions, linear motions. So this is the momentum. Then radius of gyration. So radius of gyration of a body, suppose this is a rigid body which consists large number of particles m1 and this is a distance r1 and this is m2, this is distance r2 and this is the m3 distance r3 and this is m4 distance r4 and this radius of gyration body about this axis of rotation and this is the radius of gyration body about this axis of rotation is the distance. Is the distance from a point at which the whole of the mass of the body are supposed to be concentrated, not the center mass. May or may not be the center mass. Assume that mass of the particle at this point is concentrated. Assume. And the whole mass of the body, that is m is equal to m1 plus m2 plus m3, and this mass, the distance from this point at which the mass is supposed to be concentrated, and the distance from the axis of rotation is k. K is called as the radius of gyration. When the momentum inertia of this particle, that is mk square, I is equal to mk square, that is the momentum of this particle, is the point or particle at which the whole of the mass of the body are supposed to be concentrated. It would have the same momentum inertia as of the entire body. If the momentum inertia of the particle at which whole of the mass of the body are supposed to be concentrated, may not be the center mass. Assume that one of the particle is concentrated, whole mass is concentrated at the one point, and it would have a momentum inertia is equal to suppose the one particle is rotating about the axis of rotation, its momentum is m by mr square. Similarly, if all the particles concentrated at one point, that is the momentum inertia mk square. K is the distance, and if it will be equal to I is equal to entire momentum inertia of the body. Already I have derived the momentum inertia of the entire momentum of the body is equal to m1 r1 square plus m2 r2 square plus m3 r3 square. Then I1 equating equation 1 and 2. Show equity equation 1 and 2. That is mk square is equal to m1 r1 square plus m2 r2 square plus w2. So k square is equal to m1 r1 square plus m2 r2 square plus m3 r3 square divided by capital M. So k is equal to root over m1 r1 square plus m2 r2 square plus divided by m. This is the original definition of moment K, radius of gyration. Radius of gyration has to be calculated about an axis. If you ask what is radius of gyration, it is purely meaningless. Radius of gyration body has to be calculated about an axis, because if the axis of rotation will be changed, then the distance from this particle from the axis of rotation will vary. Definitely, radius of gyration will be changed. So, moment of inertia and radius of gyration has to be calculated about an axis. If the particle consists of n number, if the body consists of n of particles having equal masses, if m1 is equal to m2 is equal to m, say, that is equal to k is the total mass of the particle is equal to n into n. So m1, m2, this the m is the total mass of the body, where m is the total mass of the body. If the particle consists of n number, if the body consists of n number of particles, that is m plus m plus m plus m. That is m into n. Because m1, m2, m3, m3, same. So m into n, that is n is the number of particles. So k is equal to m, m1 r1 square plus m2 r2 square plus m3 r3 square divided by capital M root over. So that is equal to k is equal to m into r1 square plus r2 square plus r3 square divided by capital M is equal to small m into n. Cancel. So that is equal to k is equal to r1 square plus r2 square plus r3 square. Where n is the number of particles, so the k is the radius of gyration. About the axis of rotation. Now we'll discuss the moment of inertia of a uniform rod. Going to the moment of a uniform rod, let's have an idea regarding the parallel axis theorem and perpendicular axis theorem. Actually, parallel axis theorem helps us to calculate the moment of a body of different axes, about different axes, other than the center of mass of the body. Suppose our center of gravity of the body. Suppose this is the body, and this is the axis center of gravity, and this axis of rotation passes the center of gravity, that is x dash and y dash. So IC is equal to moment of a body about the axis passes to the center of gravity. I is equal to moment of inertia of the body about an axis passes through the center of gravity of the body. Size of this body, this is the axis xy, it may be inside or may be outside the body. Most important point. It may be inside the body or may be outside at any point. But the axis must be parallel to the axis passes to the center of gravity. Most important point. This axis may be inside the body or may be outside the body. And this the distance parallel axis is S. And this the our center mass or center of gravity. If the body nearer to surface of Earth, CG and CM coincide with each other. Center mass same as center of gravity. If the body nearer to surface of Earth. And the mass of the body is capital M. And the axis of rotation I is equal to momentum of body about this axis xy. The I is equal to momentum of body about this axis is equal to summation of the momentumness of the sum of the momentum of the body about the axis of passes through the center of gravity into mh square plus mh square. Sum of the momentum of the body passes through the center of gravity and product of the mass of the body and square of the distance between two parallel axes. H is equal to distance parallel axis. So this is the momentum of body about the axis xy. I is the momentum of body about the axis xy. Now we'll discuss the perpendicular axis theorem. We'll discuss the perpendicular axis theorem. So this is the one lamina. Lamina means which thickness is very small in comparison to area. This is the lamina. This is the lamina is thickness. The thickness is very small in comparison to the surface area. This is the lamina, which consists of two axes which are mutually perpendicular to each other, x dash and y dash. These are the two axes lying on the plane of lamina which are mutually perpendicular to each other. And this x dash and y dash are the two axes lying on the plane of lamina which are mutually perpendicular to each other. At the intersection points, a third axis. At the intersection point, a third axis passes the intersection point of the two axes which are lying on the plane of lamina. This axis is z axis, z dash. So this x axis, that is the third axis, z dash. This is the third axis passes to the intersection of the two axes perpendicular to plane of lamina. That is the z dash. Because if the axis, we know that if the axis of rotation will be changed, the momentum is the same but will be different. So if the this is the irregular lamina. So if the rotate is a x-axis, if we rotate the lamina along with the x-axis, its moment of inertia is ix. If we rotate the lamina along y-axis, its moment of inertia will be iy. If we rotate the lamina along the z-axis. Z-axis means the axis which is perpendicular to the plane of lamina and at the intersection of the two axes passes the intersection of two axes lying on the plane of lamina. So the third axis must pass through the intersection of the two axes. Those two axes which are lying on the plane of lamina mutually perpendicular to each other, and third axis must be perpendicular to the plane of lamina. The two axes are mutually perpendicular and third axis also mutually perpendicular to these two axes lying on the plane of lamina. So a z momentum about this axis is Iz. So Iz is equal to Ix plus Iy. This is the Iz is equal to Ix plus Iy. Not Ix is equal to Iy plus Iz. It cannot be possible. the axis which are laying on the plane of lamina. These two axes must be laying on the plane of lamina. You cannot say that Iz plus Ix is equal to Ia. No, not at all. These two axes laying on the plane of lamina, which are mutually perpendicular to each other, and third axis must be perpendicular to the intersection of two axes, and also perpendicular to the plane of lamina. So this is the perpendicular axis theorem. Now we'll discuss the moment of inertia of a continuous body. So actually moment of inertia is a continuous body. So M1, M2, M3, these are the discrete particles. The particles which are not connected to each other, these are the discrete particles. And said momentum of inertia can be calculated for the discrete particles. The momentum of inertia is to be calculated by the summation. I have already written the particles are not connected to each other. Different body consists of number of different discrete particles. Its momentum inertia is equal to mi ri square. This is the momentum inertia mi ri square. This is the summation m1 r1 square, m2 r2 square, m3 r3 square. But for continuous particles, the particles are connected to each other. Molecules are connected to each other. In this case, the momentum inertia is to be calculated by integrations. So I is equal to what is a continuous number. This is a rod. Rod is a continuous body. Continuous distribution of mass. That is the continuous distribution of mass. And in case of continuous distribution of mass, the momentum inertia is to be calculated by that is I is equal to the summation is replaced by integrations. So that is the summation is replaced by integration. So that is called, if you take the small elemental portion dx and its mass is dm and axis of rotation ax. So this momentum inertia about this axis is equal to I is equal to dm into x square. And total length of the rod is L by taking the limit minus L by 2 to plus L by 2. And total mass of the rod is capital M. So L length, mass of the L length is M, mass of dl length is M by L into dx, and this is the dm. Dm means mass of the small elemental portion dx, and x is the distance from the axis of rotation. And putting this and limit this up to minus L by 2 to plus L by 2, we can calculate M is equal to ml square by 12. By putting this value and taking the integration, we can calculate ml square by 12. So moment as a rod about the axis of rotation is equal to about the axis passes the moment as a rod about an axis passes through center perpendicular to the length of the rods. And momentum inertia about one end of the rods. Momentum inertia about an axis passes to the one end. This is the moment. Mi means momentum inertia of the rods about an axis passes to the one end of the rods. Perpendicular to its length. On this axis we have to calculate the moment of inertia. So this is the x dash y dash. This is the center of gravity. This is the axis passes to the center of gravity. And its moment of inertia Ic is equal to already we have derived ml square by 12. And h is equal to this is the total length of rod is L and total mass of the rod is capital M. and total L is L by 2. So distance the two parallel axis is L by 2. I is equal to, applying the parallel axis theorem, I is equal to IC loss ml square. IC is equal to ml square by 12. Loss mh n by 12 the whole square. That is I is equal to ml square by 3. I is equal to ml square by 3. So momentum inertia, suppose this is the axis, this is the length of the rod SL. So we have to calculate this momentum inertia about this axis. This is the theta. So this is L, this is theta. So its component is L cos theta, and this is L sin theta. This is the L, this is the axis of rotation X. This is L, this is the axis of rotation. So this is L and this is theta, L cos theta, L sin theta. And these two planes, the rod and the axis are lying in the same plane. So this is L cos theta, L sin theta. L cos theta, as along the axis, it has no moment of inertia. If the particle is along the axis, it has no momentum, because momentum inertia is calculated about a certain distance. It should have a certain distance from the axis. If the particle on this axis, mr square r is equal to 0, it has no moment of inertia. So L cos theta, this is theta, this L cos theta has no moment of inertia, but L sin theta, this is the L sin theta, is the axis is passes to the one end of the L sin theta rod and perpendicular to its length. So its moment is ml square by 3. L instead of L, we can write it as L sin theta. So this is moment is L is equal to L instead of L, we can write L sin theta. So I is equal to moment is ml square by 3, that is m by 3 into L sin theta whole square. So I is equal to m L square sin square theta by 3. And also this rod is suppose at this rod like this. This is theta. So this is L by 2. So this is L by 2 cos theta. This is L by 2 cos theta. This is L by 2 sin theta. And this is L by 2. This is theta. This is L by 2. So this is theta. This is L by 2 cos theta. This is L by 2 sin theta. So along this axis, it has no moment inertia. So this total length is equal to L by 2 sin theta plus L by 2 sin theta, that is equal to L sin theta. So this axis, this total, this its component is L sin theta. Total along the along this direction, the total length of the rod is L sin theta. The axis passes to the center. So definite moment of inertia about this axis I is equal to m into L sin theta square by ml square sin square theta by 12. Yes or no? And the axis is axis, two rods are along these directions. This is theta and this is theta xy and this is L. The two rods and the axis are lying on the same plane. Two rods and axis lying on the same plane. That means two rods and the axis lying on the same plane. This is the axis. So this angle is theta, this angle is theta. These axis and the two rods are laying in the same plane. All are laying in the same plane. Okay. So its momentum inertia is equal to, this is L cos theta, this is L sin theta, its component perpendicular length is L sin theta. This is L cos theta, its perpendicular length, this length is L sin theta. So this is L sin theta square by 3 and this L sin ml square sin square theta by 3, one end of the rods. So I is equal to m into L sin theta square by 3, and for psi is equal to m into L sin square theta by 3 loss m into L sin square theta by 3, that is m L square 2ml square sin square theta by 3. This is the ml square sin square theta by 3, one end of the rod, and another is ml square sin theta, because along this axis modulus is 0. That is equal to I is equal to 2ml square sin square theta by 3. Yes or no? Next, last, the moment is the varieties, last variety is rod is, suppose these two axes are, these two axes, these are two rods making, they are lying on the same plane, but the axis is perpendicular to the planes of the two rods, plane of the two rods. This axis is perpendicular to the plane of the two rods. Okay, in this case, only L, its moment is about 1 end is ml square by 3. This is L, moment is about the axis perpendicular to one end and perpendicular rod is ml square by 3. This is ml square by 3, this is ml square by 3, that is equal to 2 ml square by 3. Yes or no? So write down. The axis, the two rods laying, the plane of the two rods are perpendicular to the axis, right? The plane of the perpendicular to the axis. So about this axis is modulus I is equal to ml square by 3. This is the length of the perpendicular ml square by 3, one end. This L is perpendicular ml square by 3, 2 ml square by 3. So this is the modulus, all about the modulus of the rods having different situations. Okay. Momentum in a ring, momentum is a circular ring. About an axis passes through the center and perpendicular to the plane of the ring. So this is a ring. Its momentus about this axis has to be calculated. Its momentus of a ring about an axis passes through center and perpendicular to plane of the ring. Yes. M is equal to mass of the ring. Its momentus I is equal to m r square. Momentus of ring about an axis passes through center, perpendicular to plane of the ring is m r square. Momentus about the diameter of the ring. Moment, Mi means moment. So momentum in a ring about an axis passes through the one of its diameter, any one of its diameter. So any one of its diameter, momentumness has to be called. This is the one diameter, this is another diameter. So diameter divides the ring in symmetrical two parts. This is the axis of symmetry. So if it is momentumness are calculated about this diameter, same as about this diameter, because diameter divides the ring into two equal parts. So the momentumness about this diameter same as the momentumness about this diameter. Any one of these diameters same. Any one of the diameter has the same moment of inertia. So this is the momentumness of the ring about any of the diameter. And this is the one diameter. This is IY, this is ID, and IY. This is taken as Y axis, this is ID. And along X axis, X axis, this is Ix is equal to ID. ID is the moment of inertia about any one of its diameter. Moment of ring about any one of its diameter. The third axis passes to the center and perpendicular to plane of the ring. This is the IZ. And you know that the axis passes to the center and perpendicular plane of the ring. IZ is equal to mr square. So this is IZ is equal to mr square. So applying this is IZ, this is Ix and Iy, applying the perpendicular axis theorem. Applying perpendicular axis theorem. Applying the perpendicular theorem, that is Iz is equal to Ix plus Iy. Iz is equal to mr square is equal to Id plus Id. That is 2Id is equal to mr square and Id is equal to mr square by 2. This is the moment of inertia about any one of its diameter, that is equal to half mr square. Then moment of inertia about the tangent parallel to the plane of the ring. This is the tangent parallel to plane of the ring. This is the moment ring about the tangent parallel to the plane of the ring. So this is the, you know that the diameter, this is the diameter. There is a moment as mr square by 2. So in this axis we have to calculate. So this along this axis moment says ID, this is the ID. I do half mr square ring. So applying the parallel axis theorem. H is equal to R. So and this along this axis modulus is to calculate it. Applying parallel axis theorem. I is equal to ID loss ms square mr square by 2 loss mr square. This is the 3 by 2 MR square. Perpendicular to plane of the ring. This is the momentus of ring about the tangent. This is the tangent perpendicular to the plane of the ring. This is the tangent perpendicular to the plane of the ring. This is the parallel, this is the perpendicular to the ring. And you know that the axis momentus about this axis, you know that the momentus of the axis passes center and perpendicular to the plane of the ring is mr square. And you apply the parallel axis theorem because the two axes are parallel to each other. Apply the parallel axis theorem. So, this is the axis, this is the tangent, perpendicular to plane of the ring. This is xy. This is x dash y dash. The h is equal to r. The momentus Ig is equal to mr square. So, applying the parallel axis theorem. I is equal to IC loss ms square. Suppose I will ask you what is the momentum and radius of gyration body about the tangent parallel to the plane of disk. The question is that what is the radius of gyration? The radius of gyration of the ring about the tangent parallel to the plane of the ring. Then first, your duty is to first calculate the momentum about that axis. So momentum of the tangent of the ring about the tangent. You know this momentum of ring. About the tangent parallel to the plane of the ring. That is the parallel to plane of ring is already derived the momentum inertia. Psi is equal to 3 by 2 mr square. And you know to calculate the radius of gyration, you just write down I is equal to mk square. Psi is equal to mk square. K cancel, cancel, sorry, k is equal to 3 by 2 r. So k is the radius of gyration of the body about an axis passes through the tangent, about the tangent parallel to the plane of the ring, parallel to the plane of the ring. Listen. You about suppose the radius of gyration calculate about an axis. First of all, you have your duty is to calculate the momentum inertia about that axis, and after calculating the momentum inertia, I will mk square. Subsequently, you can calculate the value of k. Next is about the center, about an axis passes through center. Perpendicular to plane of disk.
So about the axis?
About an axis passes through the center and perpendicular. This is the place center and perpendicular plane of the disk. So there is I is equal to half mr square. This R is there. About the diameter, solid disc, this is ID, this IX is equal ID, such Z S. The moment is equal to I is equal to, you know, in case of disk, it's a disk is momentaneous about an axis past the center. I is equal to half mr square. Applying perpendicular theorem. Iz is equal to this, the z axis passes to the perpendicular plane of the disk, Iz Ix plus Iy. Half mr square. Id is equal to Id plus Id. When we say about the tangent, parallel to the plane of disk, about the moment is of the parallel to the plane disk, so its diameter, moment is ID, so diameter is 1/4 mr square. I is equal to ID plus ms square. Moment say disk perpendicular to the moment of the tangent perpendicular plane of the disk. This is the disk. This is the what is about the tangent parallel to plane of disk. Tangent parallel to the plane of this part. This is the perpendicular plane of disk. This is the perpendicular plane of disk. Along this axis, moment is about an axis passes through center at perpendicular plane of disk. I is equal to half mr square. And H is equal to R. So what is the solid disk about the tangent perpendicular plane of disk? So applying the axis passes to center and perpendicular plane disk. So I is equal to IC plus MA square. This is the parallel axis theorem, applying the parallel axis theorem. Applying the parallel axis, I is equal to IC plus MA square. So IC is equal to half MR square. H will have psi is equal to 3 by 2 MR square. Then what is a solid? So moment of inertia of a solid sphere. MI means momentum of a solid sphere. About the diameter, about an axis. That is about an axis passes the diameter, along this diameter, or that is the amount is about the diameter. Solid sphere, its moment psi is equal to 2 by 5 mr square. R is the radius of the sphere. M is the mass of the sphere. And a momentum is about the tangents. These are the tangents. Along this axis is equal to we have to calculate this applying the parallel axis theorem. This is the axis passes the center of gravity IC. So applying the parallel axis theorem, these are the tangents parallel to the. This is the tangent to the solid sphere. So I is equal to applying the parallel axis theorem. Psi is equal to IC plus MA square. Psi is equal to 2 by 5 MR square plus M into R square. Psi is equal to 7 by 5 MR square. This is the amount. Suppose I will ask the what is the radius of gyration body about the tangent. You just write first of all calculate the moment of inertia. Then you write down mk square. Psi is equal to so what is the radius of gyration about this axis? I is equal to 7 by 5 mr square is equal to mk square. cancel. The k is equal to 7 by 5 into rotor. This is the radius of gyration of the solid sphere about the tangent. This is the about the tangent. What is a solid sphere? This is radius of gyration. Radius of gyration. Of solid sphere about the tangents. And last is moment of inertia of a hollow sphere. Hollow sphere about the diameter. The hollow sphere about the diameter. Its mass is m and radius is r. About this axis is equal to 2 by 3 mr square. This is the moment about an axis passes center of gravity or passes the diameter. IC, let it be IC. IC means about an axis passes center of gravity or a diameter is equal to 2 by 3 mr square. And about the tangent, radius of the hollow sphere about the tangent, so applying the parallel axis theorem. applying parallax theorem. I'm giving one assignment. I'm giving one assignment that this assignment is also in NCERT book. These are the three spheres, each of mass m. Solid spheres, three solid spheres. Each of mass m and three identical solid spheres. Radius r. Find the momentous about the axis xy. Of the system. Find the momentous system about the axis. This is the system about the axis xy. So you know that the momentous of the solid sphere is the radius r, each having the radius r. Its momentum units are I1 is equal to, for this sphere, I1 is equal to 2 by 5 mr square. And I2 is equal to this momentous about this axis, I2 is equal to 2 by 5 mr square. And applying the parallax theorem, H equal to r. So this is Ig, and applying the parallax theorem, you can calculate for this sphere, you can calculate the tangent. So I1, this is I1 is equal to, about this tangent, I1 is equal to Ig plus m square. So I1 is equal to momentum of solid sphere about this axis equal to 2 by 5 mr square. And momentum of this sphere about this tangent. About this tangent is equal to the 2 by 5 mr square, that is equal to plus mr square. Applying the parallax theorem, it is 7 by 5 mr square. And for this sphere also, this Ig is equal to 2 by 5 mr square. For this sphere also, moment inertia, that is equal to 2 by 5 mr square. And also applying the parallax theorem, H is equal to r. So moment inertia is equal to 7 by 5 mr square. This question is asked in the NCERT example of physics. An NCERT example of physics, okay? So this is I1 is, so total moment of inertia is equal to I is equal to, this is 2 by 5 mr square for this sphere, and for this sphere 7 by 5 mr square, and for this sphere applying the parallax field same as 7 by 5 mr square. So I is equal to 2 by 5 mr square plus 2 into 7 by 5 mr square. So that is equal to 2 plus 14 by 5 mr square. That is equal to 16 by 5 mr square. 2 plus 14 plus 2, 7 by 5 mr square. So this is the modulus of the sphere of the system of this axis. Thank you.